The last time we derived the Thomas-Fermi approximation, quantitatively described the screening of a Coulomb potential in solids. But again, this is semi-classical approach, and it cannot really describe the full quantum mechanical screening effect in the realistic solids or metals. So at the end of the last lecture, so I made some remarks. The second remark is that the Thomas-Fermi approximation take into account only the static charge disturbance, and it doesn't consider the time-dependent charge fluctuations or dynamic charge fluctuations. So this is a cartoon picture of what really happened in metals when we talk about the charge density fluctuations. And we know there are many ions carrying positive charge, and there are many electrons with negative charge. So we know that these two positive and negative charge are attracted to each other. So suppose there are some electrons get attracted by the hardcore positive charge ions, then this electron will get closer to the ion core initially. But there are not just one electron, there are many, many electrons. So if I take the snapshot of a picture of what really happened in the realistic metals, this is what I would see. So for a moment, because of this ion carry positive charge, it attracts many electrons nearby, so that electrons get closer to the ion core for a moment. But then this kind of process is actually overshooting. So there are more than enough negative charge electrons come close to the ion core, so that the total net charge is actually overshooting, meaning there are more negative charge than the positive charge for that second. So there are more negative charge than the positive charge just for that moment. But we know that if this is the case, the whole thing becomes negative charge cloud, right? So the red clouds carry negative net charge. So it will attract a positive charge ions to get closer to it, right? And therefore, as a result, many positive charge ions may just move, closer to that negative charge cloud, so that the whole thing becomes more positive charge again. So this is overshoot by the positive charge again. So again, so if you just encircle the big charge cloud, you'll find that this is a positive charge. And then again, this will attract negative charge electron, and you will get back to this overshooting by negative charge, and then you get back to the overshooting by positive charge, and negative charge and positive charge, and negative charge, positive charge. And this is the origin of dynamic charge density fluctuations. So locally, if you look at any place in your metal close to any ion, and the local density, charge density, is always fluctuating in time, because you could either get the overshoot by negative charge or overshoot by positive charge. So the charge density fluctuates from time to time between these two extreme limits. And there is a frequency called plasma oscillation frequency associated with that kind of overshooting mechanism. And this is a purely quantum mechanical effect, and it cannot be captured by Thomas-Fermi approximation, which assume that all charge disturbance are static. So they are standing still and they don't move. But in reality, of course they move. They follow Schrödinger equations, right? Time dependent. So all the electron wave function and ion wave function actually move in time. But the way that they move follow this kind of a mechanism. Here, that's at any second, if you take a picture, you'll find that's either overshoot by negative charge or overshoot by positive charge, and it fluctuates between these two limits all the time. So it's called plasma oscillation. There's omega p associated with that plasma oscillation frequency, associated with this physics. So we will use full quantum mechanical treatment to capture this plasma oscillations, which really happens in ordinary metals. Right, so this is the important remark. And the third remark is that the Thomas-Fermi approximation looks only at long distance behavior or long wavelength behavior. And also the assumption the slowly varying potential is valid. Okay, so remember, we consider only a very slowly varying potential in space so that the Thomas-Fermi approximation is valid by looking at only the long wavelengths, kind of slowly varying charge fluctuations. But this assumption is not valid if you look at a realistic situations where electrons in real metals are not moving slowly. And the reason why these electrons are not moving slowly is precisely because of this plasma oscillation physics that I just mentioned. Because electrons can actually move very fast from one limit to another limit of this plasma oscillations, so that the electron density is fluctuating really, really fast with a really high oscillation frequency, so that this invalidates this Thomas-Fermi approximation or assumptions behind the Thomas-Fermi theory, so that in time domain the Thomas-Fermi fails, but it captures in spatial degrees of freedom that the long tail of the Coulomb potential is cut off by this kind of a mutual inference among different charged particles. But we need to treat this in a pure quantum mechanical way. This is an interesting starting point that we could semi-classically understand this screening of a Coulomb potential. So by now, we recognize that the basic unit to construct our Hamiltonian is not going to be kind of a 4 fermion operators like Hartree-Fock. Instead, we should consider a density of electron. In the second quantized form, we should find out the representation for electron density operator. And then we should rewrite the Hamiltonian in terms of the density operator for electrons. And we try to solve this Hamiltonian in terms of the density operator, and we try to find out this plasma oscillation frequency by using this new formalism of Hamiltonian. So let's just consider the pure quantum mechanical treatment of the screening effect. Well, as I mentioned, the basic unit we should consider is no longer a single electron destruction or creation operator. Instead, we should consider the charge density. And we know that over space X, for ordinary metals, we could find that this varies in space like a periodic motions, that the charge density behaves. But on top of this fluctuations, there's kind of a uniform background charge density. But on top of this uniform background charge density, we have a small wiggle, small fluctuations, both in space and time. But let's just talk about the spatial dependence of this density fluctuations. So remember, when we talk about this electron number or electron density operator for free electron gas, this is nothing but C delta K C K, right? But here, we should generalize this electron density operator to real space because what we really need to consider is the spatial variations of the charge density. So we need to define operator which allows us to create an electron or destroy electrons in real space. So we are familiar with this momentum space electron destruction and creation operator, but we should now define the density operator in real space. And we already defined the destruction and creation operator in real space. So now we should define more formally the density operator for the electron destruction and creation operator in real space. Of course, you can guess that this, which I call this rho, this function of R, is simply just again, psi dagger r, psi of r, and this turns out to be correct, but we need to derive this a little bit. And you know that there's a relation between the real space and momentum space destruction and creation operator by a Fourier transform like this. And we know that this ck and ck dagger shows anti-commutation relations. And so we also show that this real space creation destruction operator also show the similar anti-commutation rules, except now this delta function in the momentum space, which is the Kronecker delta function in real space, it is a Dirac delta function. Okay, so the single particle potential operator that we already defined, we could also define it in real space, as we have done already. And the two particle interaction can also define in a similar way. So this is a two particle interaction, which we already defined when we defined the Coulomb potential. So the Coulomb interaction potential in the second quantized form can be rewritten in terms of say this kind of integral, and where inside the integral we have this psi dagger and psi, two particle interactions. But this the fields, destruction and creation operators are defined in real space. Okay, so we can also Fourier transform this two particle potential in K space, but here we should take advantage of this real space formula for this two particle interaction. So let's just take a short break. When we come back, we will formally define this density operator in real space. So classically, we could consider the electron density as simply just Dirac delta function. So a bunch of Dirac delta functions, which means that there's a sharp peak right at this position Ri or R prime, and there are many such places that you get charge distributions. So this is a discrete version of the charge distribution. We could consider this just a delta function, bunch of delta function. But quantum mechanically, this electron density operator is defined by this kind of integral. You could consider this as simply just in Schrödinger picture. This is simply just you perform some kind of the expression value of this number of electrons, right? And where each electron shows a Dirac delta peak at particular position R prime, and you sum over all possible electron distributions. And this is the quantum mechanical definition of the electron density operator, where psi dagger and psi are this creation and destruction operator for a single electron at position R prime. And you sum over or integrate over all the entire space of that electron distribution, and electron will appear as a Dirac delta function at any position R prime, and you simply just sum over this probability distributions of this delta peak. And if you perform this integral, you immediately see that this is nothing but this. All right, so because the delta function inside the integral over entire space, and you could simply just remove this delta function by making this R equals to R prime, so that this is the final result. Well, this is expected because this is precisely what we meant by the electron density, because this is electron density, or number of electron, which is a probability density, or number density. And you could simply just create electron here and destroy it. And this operator is what we call this number operator in real space. And we define this quantum mechanically as the second quantized form of electron density operator. Right? Very similar to what we already defined in momentum space, that you get this Fermi function like the occupation number operator. But here in real space, we simply just follow the same definition. But the non-trivial thing of this density operator is in Fourier transformation. So we can Fourier transform this and to get the rho of Q, which is this. And let me just go here. And you could simply just plug in this definition of this rho of R. But we know that this psi of R or psi dagger of R, shows the relation to the C dagger K and CK by a Fourier transformation. So you can Fourier transform this back to the momentum space and see what happens. Sum over K, K prime, I, K, K dotted R, K, C, K prime, and dr. So this is a bit non-trivial because now you have three different exponentials or two kinds of exponential factor. One is e to the iq dot r, another is e to the ik prime minus k dot r. But you could combine these exponentials and perform this integral over the r, you get some delta function, right? Which is this sum over k, k prime, delta k prime, k plus q, c dagger k, c k prime, which is 1 over volume, sum over k, c dagger k, c k plus q. And you could change your variables, you get this, k minus q, k. So now you see this electron density operator in a momentum space carry a momentum q, but this q appears in this form that this represents momentum transfer between the electron creation operator C dagger and destruction operator C. So the momentum carried by C dagger and C shows precisely this momentum change of q, and this q is precisely carried by this electron density operator. So now we have this summary of this electron density operator in real space and in momentum space. By the way, this form C dagger k c k plus q is actually the same as C dagger k prime minus q c k prime, because you can simply just redefine your momentum by shifting this k by amount of q, so that this k plus q becomes k prime and k becomes k prime minus q. So either form is okay. So they are identical, equivalent. So you can see the non-trivial formula for this electron density operator in momentum space, q, which depends on this kind of a combination. So this is some kind of a particle pair, but this is not the same as electron density operator in momentum space that we are familiar with, because precisely of this shift momentum transfer q. So this k minus q is not k. So this is not the same as n of k, the sum over k. And this is not n of k because these two momentum are different. So in occupation number operator in momentum space, this is c dagger of k, c of k. So you destroy and create the electron when they are at the same state, k. But here, the electron destruction and creation operator are not at the same momentum. So they differ by a momentum transfer q. And this is precisely what I mean by rho of q, because this q refers to the momentum transfer between the incoming and outgoing electron state. But this rho of q is very much related to this electron number operator in the following way. So we will come back to this point later. But here, we should remember that this rho of q is not the same as this Fermi function-like electron operator. So what can we interpret? What does that mean for this rho of q? Well, we can simply just consider a very simple case where q is 0. And rho of q, where q is 0, is nothing but average electron density. So if I plug in q equals 0, I get what? 1 over volume, sum over k, c dagger k, c k. And this is precisely what I meant by the electron average number, because this is nothing but you sum over electron number, occupation number in momentum space, and you sum over all possible momentum states. So this is nothing but the total number of electrons divided by volume, which is your electron density, the average electron density, because you average over the entire space. So Q equals 0 component of this row of Q should be interpreted as electron average density or average electron density. So this is nothing but you divide your total number of electrons by your volume, but what about this Q non-zero component? Then the row of Q stands for the density fluctuations. And this is related to the particle hole pair excitation. Remember, we draw this picture many times. Suppose I excite the electron inside this Fermi sphere when this electron is at state K, and then I put this excited electron outer shell out of the Fermi surface with the momentum K prime, where K prime is actually K minus Q. Suppose I have such a kind of excitation, and the second quantized form to describe such a process is precisely this row of Q. So this is actually C diagram of K minus Q and C of K. Just a single electron hole pair excitation. However, if I sum over all possible momentum states, which allows me to create such a particle hole excitation with the momentum transfer Q, then this is precisely row of Q. So now you see this connection between this density fluctuations and row of Q. So in terms of the Fourier decomposition, row 0 is simply just the zeros harmonics in Fourier decomposition of the density operator, and row of Q stands for higher harmonics components of the density fluctuations. So in terms of the Fourier decomposition, so zeroth order is simply just the average value, row 0 or m bar, but the higher harmonics of this density operator stands for the small variations, small density fluctuations. So we will come back to this later when we discuss so-called random phase approximation. But here, remember, for a single electron hole pair excitation, we can use this operator to describe such a single event. But if you sum over all possible single electron hole pair excitations, and this is precisely this row of Q. Therefore, when you excite a single electron hole pair, so you modify, you actually change the electron density, right? Because now you actually lost the electron here inside the Fermi sphere, but you increase the electron number by 1 in excited state. And therefore, electron density really fluctuates. When you sum over all possible single electron hole pair excitations, you describe the full charge fluctuations near the Fermi surface. And that is precisely what it means physically. That describes the density fluctuations of electrons near the Fermi surface by summing over all possible electron hole pair excitation. Okay, and this is precisely what we need, because what we need is to use the second quantized fields to actually reformulate the Hamiltonian in terms of the density fluctuations. Okay, so the Hamiltonian of a Coulomb interacting electron gas can be reformulated in terms of a row of Q, which is the density fluctuations. And of course, you can understand why we really resolve this failure of Hartree-Fock, in the sense that the Hartree-Fock doesn't include the spin correlations from the opposite spins, right? But here we do have such correlations, because remember, rho is actually, in terms of the real space language, this is nothing but psi dag of r, psi of r, but you need to sum over spins. And later we will show that the Hamiltonian for Coulomb interacting electron gas is a function of rho of Q times rho of minus Q. This is a potential term. You sum over Q. And there's a 1 over Q squared here. So this is the thing that we need to prove, but let me just show you the results first. So the result is that the potential term, the the Coulomb term can be expressed in terms of this density-density operator multiplied together. So you get rho of q times rho of minus q in a potential term multiplied by this Fourier transform, this Coulomb potential term, 1 over q squared. So now you can see that we do have the interaction between different spin species because each of this term represents the particles c dagger of k prime c k up plus down. And likewise, you get this c dagger up, c up, plus c dagger down, c down, with the different momentum. So by multiplying the rho of q by rho of minus q, you can immediately see that you got cross term, right? You got a term where electron operator carries spin up and a term where electron operator carries spin down. This is exactly what we need because in the Hartree-Fock approach, we do not have such an interaction between spin up and spin down electrons, but we do have right here because when you expand this product, you get 4 terms: up, 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 down, and down, up, and down, down, right? So if you look at the term that you multiply the spin up operators by spin down, this is precisely the interaction between spin up and spin down electrons, which is already included here, which fixes the failure of a Hartree-Fock, which fixes everything. But we need to really derive this form. But this is our next job. But I'll tell you the conclusion. The conclusion is that by introducing this density operator or density fluctuation of electrons, we can reformulate Hamiltonian in terms of the density-density product. And in that product, we do have included the interactions between spin up electrons and spin down electrons, which fix the problem of a Hartree-Fock. And by studying the time dependence of the density operator, we can understand why the electron density will fluctuate back and forth and get this kind of a plasma phenomena, right? So that's our next job. So this is just tell you that it is indeed a correct starting point to treat this, to study and understand this, density fluctuations and plasma oscillations and Coulomb screening effect by using the correct language. So once we choose the correct language, and it's very easy to solve this difficulty. But the most difficult is to find the correct language or correct basis. So this is the most difficult part. But once we identify the correct language, and everything's as follows. Okay, and this is an important lesson. If we miss this correct ingredient, say the electron density, you will miss everything, just like Hartree-Fock. But if we simply just get the correct operator basis, then everything is straightforward and without any inconsistency. So time is up, so let's stop here. And next time we will derive this Hamiltonian of a Coulomb interacting electron gas by using the density operator.